Okay, good afternoon, everyone, and welcome to today's Wednesday seminar. It's my great pleasure today to introduce our speaker, Tom Gurr, who is an associate professor in this department since August.
Yes.
Before that, he spent 4 years on the faculty at the University of Warwick, and he obtained his PhD at the Weizmann Institute under the supervision of Oded Goldreich, before spending a postdoc year at Berkeley. He has been working on aspects of complexity theory and quantum complexity in particular. And I think his work is marked by bringing in novel, innovative uses of mathematics to the study of quantum algorithms. And this is what we're going to be hearing about today, quantum algorithms and additive combinatorics. Over to you, Tom.
Thanks, Anuj, for the kind introduction. So I'm going to talk about line of works joined with several collaborators, Vahid Asadi, Igor Shinkar, Sasha Golubnev, and Satya Subramanian. And this is very much part of an ongoing research endeavor I'm very much invested in. And I wanted to start this by two motivating quotes. So the first one, by Rota, says that, well, every mathematician has only a few tricks which they use time and time and time again. So I want to tell you about one of mine. And the second one, by Polya, says that an idea which can only be used once is a trick. If one can use it more than once, it becomes a method. So I'm not going to tell you about my trick, I'm going to tell you about my method. Okay, so I'm going to talk today about quantum algorithms, but I promise that I'm not going to assume any preliminary knowledge about quantum computing. So this slide is going to capture everything that you'll need to know about quantum algorithms. Essentially, the quantum algorithm works. We have a bunch of qubits. These are quantum bits, the analog of a classical bit. We feed them into a circuit. It is a unitary matrix, but we don't really care for all intents and purposes now. And at the end, we measure and we get the output. So just like like a classical circuit, only at the end you measure and you get some statistics. And I want to give 3 examples where quantum algorithms are really, really good at. So the first one is finding subgroup structure. And the most famous example here is Shor's famous factoring algorithm. While Shor's algorithm factorizes an integer, the way it's being done is by being able to find subgroups. The second one is rapid mixing of Markov chains, and this is a fancy name of saying that we can speed up certain probabilistic models. So in particular, Grover search is maybe the most famous example, where we can find a needle in a haystack faster than one could do in a classical world. And the last one, which is arguably the one characterizing property of quantum algorithms, is that they are really, really good at computing Fourier transforms, exponentially better than classical algorithms. And a lot of the power of quantum algorithms come from this power. So what will happen is that we will assume in this talk that quantum algorithms have these magical properties, and using that, we can see the entire framework. Okay, so this is going to be the high-level motivation slide. So I keep getting, when talking to researchers who are on the physics side, that the biggest challenge that we currently have in quantum computing is to build a quantum computer. And I can agree with this statement. However, I think just as challenging is, given a full-blown, large-scale quantum computer with fault tolerance, what can we do with it? And the reality is that it is extremely hard to find ways to construct quantum algorithms which are fundamentally different. And in many ways, the 3 examples that I gave in the previous slide sort of capture a large fraction of the type of algorithms for which we can get quantum speedups. And so most algorithmic work in quantum computing tries to see, can we do better than these 3 sub-procedures that we know how to do well, beyond just generalizing them? And my goal for the next decade or so is to find a way to make that process of finding and discovering new quantum algorithms easier. And I want to give an example of a high-level paradigm, very abstract. We can take a weak quantum algorithm, have some machinery that boosts it into a strong quantum algorithm, and then in a way we can reduce the problem of creating these full-blown quantum algorithms to something which is hopefully much easier. And now I'm going to make this precise. So this is the exact type of boosting that I want. It's a boosting of knowledge. It starts with this key question. Suppose that we know how to solve a problem on a small fraction of instances. Can we derive how to solve them all instances? So, for example, while I was working on this paper, just as it's an example that happened, I have a child in primary school. He was learning how to, I thought it would be nice to teach him how to multiply matrices. So he actually enjoyed that. So, in the beginning, I tailored this really, really specific example where the number adds up beautifully, and I was very pleased to see that he gets the idea quite quickly. But then when you go and actually try to solve real matrices, then the computation gets hard, and most of the time he would make a mistake. So the question is, if you can only solve a problem on specific structured instances where things are allegedly easy, can you lift this ability to do minimal amount of ability of solving something into a full-blown ability to solve the problem and the worst case? And in fact, I want to today to focus on specific type of problems, which are linear problems. So under the right extension, it can capture matrix multiplication. It can also capture things that we care about, like computing Fourier transform. This is, so if we have a matrix and it's the van der Monde matrix. But I want to say, what do I mean by a linear problem? So a linear problem is characterized by a set of matrices. And the matrix M is the definition of the problem. For example, and we can play with that, it could be a running example. The van der Monde matrix is the matrix when you feed a vector and you get its Fourier transform. So, we fix one matrix, any matrix, and we want to solve it. So the problem, given a vector x, and here we will be over some finite field f, the goal would be to compute m times x. Now, abstracting this, formalizing what's written in the yellow box, now suppose I'm giving you an algorithm that only rarely succeeds. So for example, here you can think about the probability over a choice of a random input that the algorithm will be able to multiply to solve the linear problem. Hence, compute m times x is only alpha. And let's think of alpha to be, let's say, 0.01, so only on 1% of the inputs. Then the question, can we boost this alpha into 1? Can we take an algorithm that can only solve an alpha fraction, a small fraction of the inputs, and make it solve all of them? And the main result, what I'm going to prove today, mostly, is we'll take some quantum algorithm, and for any linear problem M that can only solve 1% of the inputs. And I'll show you that there exists another algorithm with similar complexity. It would slightly blow up the complexity but by a tiny bit, that can solve 100% of the inputs. And in fact, this alpha is not just 1%. It could run polynomially to 0. So it could be that you can only solve the problem on such a tiny, tiny, tiny fraction of the inputs. Yet even though you can only do this highly limited algorithmic work, you can boost it entirely. So that's the statement. And I should say that please interrupt me at any point if something is not clear.
Okay.
Yes?
So for this to be the boosting thing, you want this alg prime to be easily computable from alg. You want
Yes.
the conversion of the algorithm itself to be
Exactly. So here comes the factor of how many gates, which is analogous to the time complexity. So it means that we will only pick up a factor which is like n to the 3/2. So if your problem, in general, solving a linear problem takes n squared. And so it means that as long as you're doing something which is of complexity which lies between this paradigm, then you can get a better algorithm. So in any algorithm whose complexity is at least n to the 3/3, you can do it at essentially negligible cost. However, if the algorithm runs somehow in linear time, then this is...
Yeah, but my question was slightly different. I mean, alg prime is not much more complex than alg, but you want to be able to do the conversion automatically, right? You want the boosting, I mean, you don't have to...
You mean the reduction itself from alg to alg prime?
That's right. You don't want to have to work.
Yes, to work in, and in fact, that's a good point. The reduction itself run in time, which is proportional to the amount of gates. So everything is with overhead of n to the 3/2. Thank you. So I want to start and show you how this can be done in a much easier case than what I'll actually show soon. But this is a one-slide explanation just to give how this is at all possible. So what I'm going to do here is, instead of assuming that the algorithm succeeds on a negligible tiny fraction of the inputs, I'm now saying that the algorithms can succeed on 90% of the inputs. So now the goal is only to go from 99 to 100%. And the idea is going to be something which is called linear local correction, which is a very simple idea, which I think it's a trick worth seeing. It's inspired by work of BLR from the 90s. So the idea is, okay, we have our original algorithm algem, and now we want to boost it so it would work on 100%. I'm going to start by drawing a uniform random vector R. And then I'm going to take my input V and write it as a linear combination of R and V minus R. Okay, what did I achieve by that? What's happening now is that R is uniformly distributed, and V minus R is also uniformly distributed if you look at them in isolation. And therefore, if I take my original algorithm, which succeeds with probability 90%, and I apply it both to R and in V minus R, then assuming that the algorithm got R correctly and V minus R correctly, then the probability that I'm going to get the correct multiplication is 90%. Now, here, this could be a confusing point, because randomness here is taken over two different aspects, so let me clarify. You can say, we started with 99 and now we're back to 90, so what is going on? So the algorithm itself is correct on 90% of the inputs in the beginning. So there could be like a particular input that the algorithm will always get wrong. And then what we're getting is an algorithm that here is correct on any vector, and the probability in which it is correct is 90%. Of course, one can repeat it and amplify and get the algorithm to be, the success probability to be arbitrarily close to 1. But the idea is, if you're thinking about quantum algorithms, the output is always randomized. And so the idea is not to get the algorithm, to avoid the randomness of quantum mechanics, but rather just to boost 1% of the inputs into 100% of the inputs. Okay, so this is the simple idea that underlies this approach. However, when we're trying to think about the more interesting regime, algorithms that only succeed, let's say, on 1% of the inputs, then things break in a fundamental way. So what do I mean by that? So this is an example that we've seen early on when trying to move from the 90% regime to the 1% regime. So suppose that we were walking over the finite field with two elements, and by that, this is like for computer scientists, we care about bits. It's a very natural thing to do. So I want to consider an algorithm that is only correct on inputs where the first bit is 0. Okay, so, and otherwise it returns some junk, let's say just 0. So the correct inputs are the ones where the vector that we want to compute start with 0. So because this is, we're working over GF2, this is a half space, so it means that our algorithm is only correct on 50% of the inputs, so even better than 1%. But the point is that if I have a vector that starts whose first coordinate is 1, hence the algorithm is wrong, and now I want to decompose it into a sum of two components, as we did in the slide before, then one of these components must be 1. And so there is no chance that we will, so we can roll the dice again, but we hit a roadblock here. And, at first it seems that all hope is lost because this looks like a very big barrier. But luckily, this is where additive combinatorics comes to the rescue. And I want to tell you, I want to butcher additive combinatorics in a slide, just to give you my interpretation of it. The idea in additive combinatorics is to study approximate notions of algebraic structures. And what do I mean by that? So for example, one of the things we care about a lot is group structure. And additive combinatorics can provide a way which doesn't involve any algebra and can approximate the notion of a group. So let me explain maybe the most famous example of object we study in additive combinatorics. We have the definition of a sum set. So the sum set of, you have some set X, and the sum set is all combinations of adding one element and the second element from that set. And more generally, it doesn't have to be only two elements. It could be adding together 3 elements, 4 elements, and so on and so forth. So the idea that this provides a combinatorial analog of an approximate subgroup structure. So what do I mean by that? The defining characteristic of a group is that if you add 2 elements in a group, you remain inside the group. The sum set tells you, in a way, if you take your set X and now you add 2 elements of the set, the larger that the sum set is, the more you're getting outside of the group, which means that outside of the set, which means that you are less of a group structure. And the smaller you are, it means that you have exact group. So for example, if the sum set is equal to, if X plus X is equal to X, then it means that all additions will always remain in X, and so you have group structure. And another way of looking at it, if you look at T times X, it's like combining T elements. So if T is arbitrarily large, then this is a linear combination, an arbitrary linear combination, and then you have subspace structure. But if you're looking at the smaller combinations, then you get some approximation of that. Okay. And now I want to tell you about a very powerful lemma, which I genuinely think can be applicable in so many areas in theoretical computer science and perhaps beyond. So let me say it's called Bogolyubov-Ruzsa's lemma, and in fact we'll need some strengthening of it, but let me just try to explain what's happening here. So I have a set X of density alpha. So I especially try to create, to draw the ugliest non-structured form that I can. And you can ask, what type of, what is the subspace, the largest subspace I could find in my shape? So I have a shape, it has no structure at all, and I want to find linear structure in it. And generally, the only type of linear structure I could get is very small. But what Bogolyubov's lemma tells us that if I'm considering the sum set of 4 elements, so combination of the form x1 plus x2 plus x3 plus x4, then this smoothens the set, and it looks a bit nicer, and then it admits a subspace which is very, very big. And as you'll see soon, the power of quantum computation comes from the linearity of quantum mechanics. So being able to have large spaces, subspace structure is key. So, and by the way, this innocent, so how large the subspace is, so, we started with a set of density alpha, so the dimension, like the codimension is going to be 1 over alpha squared. And in fact, if one wants to go better than that, and improve this exponentially, then that amounts, and this is a celebrated result by Sanders, which is called the quasi-polynomial Bogolyubov-Ruzsa. And very recently, the polynomial Fremer-Ruzsa conjecture was proved, and so we know that this can actually be done essentially with a log factor. You might ask, why does it matter? This is exactly what's going to allow us to go from the 1% regime into algorithms that only succeed on a fraction of inputs that tends to 0 very rapidly. Okay. So I want to show you how we can take this simple variation, like this simple Bogolyubov lemma, and use it to boost algorithms that are correct on 1% into algorithms that are correct on 100% of the inputs, and avoid the barrier that we've seen before. Yeah, yes?
Just before you do, what's the significance of the number 4?
So Andrew was asking what is the significance of the number 4. So if we are doing...
Suppose you did it with FP rather than X2, is there a lemma for that?
I agree, and conceptually I would say that, 4 is not a number that appears in serious math, right? I mean, 2 should be the right number. But if you look at, so if you would tell me, can we get smoothened just by getting 2x, then there's a very easy counterexample. It's sort of the Boolean hypercube bounded by a certain threshold. Then you might say, okay, fine, 2 is not good, maybe 3 would work. And 3 would work if we are over f2 to the n, but it would break for any p which is larger than that. And therefore we'll, but if you reach, but if you're going for 4 elements, then you're good. In a way,
So it works for
any finite field, and in fact it works for any abelian group. So it's very general, and with the exception that 4 becomes 2x minus 2x. But these are some minor points. Okay, so, but let me try to kind of explain how the trick, what the idea is. So I have this algorithm, it's successful only on an alpha fraction, let's say 1% of the inputs. So again, like this is, and let's denote by x the set, the set of inputs which are valid, the good inputs. Okay, so this is a set of density alpha. Now, I didn't choose this notation by coincidence. It exactly fits the Bogolyubov statement. And this allows us to extract this large subspace V, which is roughly the same size of V. And because this is a subspace of 4x, then it means that every element of V can be written as a sum of 4 elements. Each one of them belongs to the original subset of good inputs. So it means that any vector in V, I can write it as a linear combination of 4 vectors which are good. And hence, we win, in a way. However, there are fundamental problems here. The first one is, I told you that you now get, you get this vector, and there is a combination of 4 elements that you can compute correctly. But how do you find them? How do you get these elements? And more than that, so far I told you there is this set X where we succeed, and now there is another set V where we succeed, but what do I do outside of this V? How do I solve it on 100%, right? If V is roughly the same order of X, then did we gain anything here? So let me discuss both of these. So first of all, we need something which is stronger than the vanilla Bogolyubov statement. I'm not going to state the full lemma. I just qualitatively explain what's different. It will be robust in a way because quantum algorithms are very noisy, and so you have to have some flexibility. it would be probabilistic in the sense that it would enable us to randomly get a decomposition, and it would have the better dependency that comes from the harder machinery, the additive combinatorics machinery. So I'll give a simplified version of this lemma. So again, we have a subset which is unstructured of density alpha, and we'll get a subspace. Now we will be able to extract a subspace, but note that now the dependency on alpha is polylog as opposed to just 1 over alpha, which is why this is called the quasi-polynomial Bogolyubov-Ruzsa as opposed to just the previous one. And the key thing that we need for the purpose of the talk is, whereas before I said that there is one decomposition, that you can decompose V into a sum of 4 elements, now the argument is there are a lot of decompositions. So if you manage to get 3 elements out of the good set and you just sum them together, then with probability, at least alpha squared, you'll have the sum of x1 plus x2 plus x3 plus x4 will sum into your vector. So it just says that there are many, many, many these type of decompositions, and hence one can sample them. How? We'll see in a moment. So just to complain and then give two problems with this lemma and why we shouldn't be happy so quickly. First, again, it's not clear how to amplify success probability. When we're thinking about success probability, which is 2/3, then you repeat, and rule by majority. Now, if you have an algorithm and it's correct its probability 1 over n, then you compute and you just get junk. So the vast majority of the answers would not be correct. So it's not clear how to amplify, what to do with this alpha squared. And 2, here I'm telling you, well, just sample 3 good elements, but we don't know. We don't know whether the algorithm on which inputs the algorithm give us the right answer, and on which inputs it doesn't. And this is where the quantum, and of course, perhaps a crucial point, we don't even know what this subspace V is. So how do we know which vectors we need to decompose and so forth? Okay, so this is where quantum algorithms come to the rescue, and this is, we have these 3 procedures. I'm not going to go into the details of how they're proved. I'm just going to tell you about what they're doing. So the first procedure allows us to verify the correctness of the algorithm. So what does it mean? So this cat notation is just a quantum way of saying I take a vector V and I feed it to my algorithm and I get the answer of the algorithm. But the way that things go in the quantum world, you can do it in superposition. So you sum over all possible vectors, and you can imagine that the quantum computation sort of works on all of them in a way simultaneously. Then we'll have this circuit. And what the algorithm will output is the exact same vector, only it would annotate each one of the vectors that the algorithm outputs with a flag indicating, is this the correct answer or is this a false answer? So in some sense, it just, whereas before we didn't know where the algorithm succeeds and where it fails, now this allows us to have that information. And the size of the circuit is this O of n to the 3/3, hence the blow up in complexity potentially. And I want to just give you a hint. I mean, this might look magical, but it's actually the underlying idea is simple. How is that possible? So the first observation to make is if I have a matrix times, and I want to compute m times v. So computing a single coordinate, this is an operation that I can do in linear time, right? Just like by matrix multiplication, as I taught my son, you just go over 2 lines. And then you can construct this oracle. You can say, for every coordinate I want to have an oracle that tells me whether the multiplication is correct. So what do I get? I get this like error syndrome type of vector, which will give me 1 wherever things are correct. And now, in order to know whether the algorithm is correct or not, I can do a Grover search, because now I want to find a 1 in a sea of 0. Now, of course, this is more complex because we have to do everything in superposition and there's no measurement, but that's the high-level idea. And the moment that we can verify correctness, then now we can amplify the probability. Because, suppose something is correct with probability 1%, so we can run until we see that we got the correct answer, and then we're good. Okay, the other algorithm will enable us to sample from the good set X. So it's an algorithm that synthesizes a state, which is a uniform superposition over all the good inputs. And then if you measure it, you get a uniform random good input. So this will allow us to get inputs from X. And the last one, it's for us to be able to learn this like subspace V, the structured Bogolyubov subspace. So it's an algorithm so the subspace is typically being characterized by its Fourier decomposition. And I won't get into the details here, but the idea is that we learn these Fourier coefficients up to a certain precision. And so we obtain some approximation of the linear subspace. In general, any subspace is being characterized by having very concentrated Fourier spectrum. So so to find the subspace, you need to fish for heavy Fourier coefficients. Okay, so this is a bit like these are the 3 black box pieces that we'll have to take for the sake of time. And I'll just show you how to use them, these 3 quantum magical powers. Okay, so let's recap the strategy and see how everything fits together. So we had an algorithm. We had a set X, which is the inputs on which we compute correctly. And then we have the Bogolyubov subspace, which is what we get from the additive combinatorics machinery. So we're going to do a simple case analysis. If the input that we're trying to solve now is part of X, i.e. the set of good inputs upon the original algorithm is correct, then we're done. There's nothing to be done. We can just run the algorithm. If the algorithm gets a vector which is in this Bogolyubov subspace, then we will do this local correction by Bogolyubov's lemma. I'll quickly in a slide just explain how this works. So the way it works, this is just restating the Bogolyubov lemma, so for convenience. We apply this lemma with respect to the set of the good inputs, and we use the sampling algorithms to get 3 random inputs from the good set. And then the statement tells us that the probability over these 3 x1, x2, x3 from X that we sampled, that we will get the 4th element that would sum to V is at least alpha squared. And so if these events happen, then what are we doing? We take the algorithm, the original algorithm, we run it on each one of these good xi's that we sample, which would just give us, this is an algorithm that is correct on the elements in X. So this would just be the sum over mxi. Now by just linearity, we can sum the xi's together, and then we get V, and we get what we want. And of course, you might say, okay, so we'll get a valid decomposition, but we will get it with probability alpha squared. But now, because we have the quantum algorithm that can perform verification, then we can just repeat until we reach the right solution. So, okay, so, if the vector was in the subspace, we just run the algorithm. If it is in the Bogolyubov subspace, we can locally correct it. But if it's not in any of them, this is where, things might seem a bit fishy. Did we gain anything, right? I started by telling you there's this set, X, it's 1%, and then we managed to find this set V, which is roughly the same size of X, still 1%, on which we are correct. But what happens with the remaining 98% of the inputs? So what did we even gain here? We started with a set of density alpha, We got maybe even a smaller density, but we got linear structure. And now, this is the crucial point. And the idea is that now that we have the subspace as opposed to an ugly set with no structure, then the idea would be to imagine that on the right hand, this is the space of all possible inputs. So before we had an ugly shape. So if we want to sort of tile the space, we need to do many shifts because there are lots of points of intersection. Whereas if we have a subspace, linear structure, which is sort of like a symmetric cube, then the tiling this is a coset structure. It's completely independent. So the amount of tiling that one needs to do is very, very small. And this amounts into a very simple linear algebraic claim that you can use the Bogolyubov type of decomposition, but now you can decompose any vector at all in f to the n and write it as a sum of 4 good elements plus some sparse shift. So plus some vector s of Hamming weight, which is constant. And since we want to, we can always multiply by a vector. If it's a sparse vector, then multiplying a sparse vector by a matrix, it's a very cheap computational task to do. You can do it in linear time. And then having this sparse shift means that, so we can compute, as before, the algorithms here to get mx1, mx2, mx3, mx4. And we can also do m of the sparse shift, ms, very cheaply and just get the answer in general. Okay, and now there is one small thing that one needs to say. In order to be able to shift the subspace, to tile the space with the subspace, we need to know what the subspace is. And this is again where the quantum algorithms come, where we can learn the exact description of the subspace, and then we can arbitrarily shift things to it. And just to say maybe in a word here, that I mentioned that there are these 3 things that quantum algorithms can do well. And in fact, we've used all of them here. So this is not, in a way, this is not a coincidence. And I want to end by, talking about a couple of open problems and maybe, if you'll tolerate, some philosophical musing. So the first question that you might ask is, well, okay, this is great. We took a quantum algorithm that is only correct on 1% of the inputs and made it into one that is correct on 100%. Why can't we do the same with classical algorithms? And the point is that we can do it, but for very, very specific and structured type of problems. Whereas for quantum algorithms, we can go for all linear problems, and as I'll mention soon, maybe even way beyond linear problems. And at least my perspective on that is that these exact 3 things that quantum algorithms do well are a bottleneck for classical algorithms. And this is, the classical boosting can only happen where stars align and the problems that are now being solved quantumly are somehow classically easy, given the particular structure of the problem. So this is the first thing. The second one, we can ask, can we go beyond linear problems? How far can we take it? And so this is part of what I'm trying to do, and there are some upcoming works that extend this to quadratic function and perhaps beyond. And finally, there is another regime that is very interesting in the quantum setting, where you can take an exponential amount of information, you can encode it in a quantum state, in the amplitude of the quantum states. This is this is done quite commonly on for example, in the HHL algorithms, which solve linear equations. And this is a potential where quantum algorithms can really shine and get exponential speed ups. So the question whether this type of machinery can work there. Yes, and that's all I wanted to say today. Thank you for your attention.